Electronic throttle control. So electronic throttle control has been around for 20 years or so. Manufacturers in the past would have a cable that ran from your gas pedal to your throttle plate. That system's been completely eliminated. So now when you push on the gas pedal, you are no longer in control of the actual position of the throttle plate. It might sound scary, but there's actually a lot of benefits. And the main thing here is we can reduce the amount of redundant components and systems on cars. We can simplify a lot of these systems. So in the past, when you pushed on a gas pedal, you had a cable that was attached to the throttle plate. That cable was a mechanical component, and they did wear out over time. And so that's not a main issue. It's not a major issue with those older systems. But if that cable were to become frayed, it could actually jam up and hang a throttle plate. So you can have a vehicle that you push down the gas pedal and the throttle opened, but the spring on the inside of the throttle plate wasn't strong enough to pull back on that cable. And you can have a car that like ran away. There are some other things on the older style systems that just, or more or less, were like efficiency type problems. So as cars become more and more advanced, we have more and more systems on these vehicles. So take, for example, like traction control. Traction control is a system that monitors wheel speed and tries to detect loss of traction. So a lot of these cars have a button you could push to turn the system off. If you have a sports car, you probably push that button every day when you hop in the car. But traction control is attempting to eliminate a accident scenario. So when you maybe are taking a turn a little too sharp with a little too much gas pedal, pedal position on a slick road, you're going to start to slide a little bit. And what that system's going to do is it's actually going to snap the throttle plate shut. So your gas pedal position, your accelerator pedal position might be at 50%. But as soon as you start to get a little bit of wheel slip, that system's going to close the throttle plate and completely ignore the fact that you're still pushing on the gas pedal. So these systems also have some other, benefits to them. Like take, for example, cruise control. In the past, cruise control was an entirely separate system. It was an additional cable, an additional actuator of some kind. They were vacuum controlled or they were electronic motors, and they pulled on a cable. So you had two cables that were attached to the throttle plate. One was going down to your foot and the other one was going to a cruise control motor. So the cruise control systems have been simplified because we have a computer controlling a throttle plate now. And if we turn on cruise control to maintain 70 miles an hour on the highway, we don't have to have a second system actually pulling the throttle plate open and close. We can just simply use the same system that's already there. The electronic motor that's on our electronic throttle plate can just be commanded open a little bit or close a little bit to maintain vehicle speed. Idle air control. So we talked about idle air control in a previous chapter. On your cable style systems, there had to be some sort of stepper motor that would allow for a controlled vacuum leak. I call it a controlled vacuum leak because it's a bypass of the throttle plate. And so when you went to turn the air conditioning on at a stoplight, in order to prevent the engine from stalling from that extra load, the idle air control system would step up and allow a little extra air to bypass the throttle plate, which would allow the engine RPM to remain the same. We can completely eliminate idle air control systems with electronic throttle control because, again, we have a computer that has full authority and full control over the throttle plate. And so when you turn on the air conditioner or you're parallel parking and you're going to cause a whole bunch of resistance on a power steering pump, the computer can just bump the throttle plate up a few percentage points in order to maintain the correct idle speed. So we can eliminate idle air control systems completely. We can eliminate cruise control systems completely. Those are two systems on a car that no longer exist once we install the electronic throttle control system. Let's talk about pumping loss for a second. The chapter goes over pumping loss briefly, but what pumping loss is, it's the restriction that we see, and we call it vacuum. So if you think about how an engine works, we have a throttle plate that's causing a restriction. And as we open the throttle plate, we allow more air in, and we reduce that restriction. And so what happens to vacuum as we open a throttle plate? Vacuum goes away. Well, when the engine's running and it's operating in a vacuum, like a high vacuum mode, like a status, that restriction is actually robbing efficiency from that engine, because the engine has to create some power to keep itself moving. And so the vacuum is inadvertently causing an efficiency loss, fuel economy loss of that engine. Some of that energy has to be sent just right back to the crankshaft to keep the engine rotating. And so when we're on the highway, this is where pumping loss strategies come into effect the most. So what manufacturers will do when you're cruising down the interstate and you don't need a lot of engine horsepower, they'll actually open the throttle plate more. So if your pedal is at maybe 20%, the throttle plate itself can open up multiple times that. It can open up, in theory, to 100% without the engine accelerating. And it goes against, that theory goes against like our common thought process and how throttle plates directly react, how engine RPM directly reacts to throttle plate position. Excuse me. So what these engineers do here is they allow the throttle plate to open more, which reduces engine vacuum. But in order to combat an engine accelerating in that scenario, what they do is they detune ignition timing, they retard it, so they have ignition timing happen not as advanced. So normally you'd maybe be at 20 or 30 degrees ignition point before top dead center on your power stroke. They'll bring it closer to zero, which actually reduces horsepower and slows the engine down. The other thing they'll do is they'll reduce the amount of fuel that's delivered. They'll lean the engine out. And so in a combination of those two things, when we control ignition and we control fuel, we can open the throttle plate a little bit more and not accelerate the engine. And so it's a minor efficiency gain, but it's enough that it's worth noting. That is a benefit to manufacturers, because anything we can do to increase fuel economy matters. Even if it's only going to increase fuel economy by 1 mile per gallon, it still matters. With CAFE standards pushing us to 55 or so miles per gallon here soon, manufacturers are looking at every single option on the table. So electronic throttle control allows us to eliminate cruise control. It allows us to eliminate idle air control. It gives the computer control during safety situations such as loss of traction. And it also helps on the fuel economy side. So when we're thinking about like the scary thought of when you push on the gas pedal, you don't have control anymore, you have to weigh out the benefits versus the potential scary situations. And so what the scary situations are, if you don't have control over the throttle plate and a computer has control, what happens if the computer commands the motor to the wrong position and gets confused and opens the throttle plate up when you're not trying to accelerate? Toyota had an issue with this, and there's plenty of articles on the internet you can read. But Toyota had a problem in the mid-2000s. I can't remember the exact dates. I think it was late 2000s, closer to like 2008 or 9. They had a problem with a few cases where these cars actually ran away. And so on the highway, and there were fatalities definitely that were caused by this. You had engines that just went to wide open throttle, and you had panicked drivers that did not even consider popping these cars into neutral or trying to shut them off somehow. You got to remember, a lot of these cars are push button now. There's no ignition switch. And so you had a runaway situation that took place. And that's probably the biggest thing to be fearful of with this type of system. But manufacturers have put a lot of redundant systems in place now. And there's actually been federal laws that have been passed in order to implement safety control devices. So, for example, the one safety law that comes to mind is, I believe it's on 2018 model year vehicles and newer. If there's any brake pedal input, so your brake pedal is pushed, it goes to a body control module, it gets broadcasted across all the modules on the car. If there's a brake pedal input at any time, the throttle plate must close. And so it goes without saying that makes sense. If you hit the brake pedal, you're probably trying to stop. But now it's become another safety feature. So if the computer, for some reason, had bad data, so if it thought that you were actually trying to accelerate, if for some reason there was a wiring issue and the accelerator pedal data was commanding to the TAC module that the driver wanted 100% throttle, it doesn't matter where the throttle is or what data is coming down the line. As soon as the brake pedal is pushed, the throttle plate is closed. That is a law. That is on all cars. And you have to keep that in mind, because now when you go to do like install diagnostic test, let's say you want to check for ignition misfire and you want to load the engine a little bit. Well, typically what we would do is put the vehicle into like a stall test where you'd drop it into drive, push on the brake pedal really hard, and then give it some gas. You can't do that anymore unless you go into a scan tool and actually enable a stall test. So you can still do this test, but you can't do it without a scan tool, because as soon as you push on the brake pedal, you get zero acceleration out of that engine. Let's see, what else is in here for tip-in? This one right here. Another benefit of your electronic throttle control system is the design of like how we implement full throttle. So engineers can now set up the software in such a way that when you slam the gas pedal to the floor and you go to 100% acceleration, there's a delay before the throttle plate actually opens. Since there's no cable, you don't get that violent burst of oxygen that enters the engine. And in the past, the problem with this was we'd get a potential little hiccup to the engine. So when you push down on the pedal, you'd get kind of this little bog or a not smooth transition to full throttle. And the reason you'd get that hesitation or a little bog and hiccup in the engine was because you were increasing the amount of oxygen very quickly, and the computer had a delay before it can actually get the fuel ramped up to match that oxygen. And so now what engineers have done is they've designed this tip-in mode that delays the throttle actuator from opening. It opens the throttle plate slower. So you might ramp the throttle up very quickly, but the pedal does not give the exact reaction to the plate itself. So the throttle plate kind of opens slower, so that way the fuel has time to catch up. And so you get a better experience as the driver of the vehicle. You don't get that bog. Your accelerator pedal position sensor is what gives feedback to the computer. So when you, the driver, push on the gas pedal, you are rotating a potentiometer. And so inside the throttle components themselves, there's an accelerator pedal position sensor. There's typically two. And you're going to notice that this is a trend. There's 2 APP sensors and there's 2 throttle position sensors in the actual throttle body itself. That is a part of the safety features for redundancy. So in the event you have some sort of sensor go haywire, goes AWOL, and puts out bad data, the computer is always going to reference both of those sensors and make a determination on whether or not it's going to trust that data. And so the sensors have to be putting out rational information. And if there's a situation where data gets skewed, like a voltage drop issue, and now you're off by a half a volt from one to the other, the scaling is different, the computer will go into a limp mode, a reduced engine power. And how manufacturers accomplish this, the strategies they use, it does depend a little bit from one manufacturer to the next. So typically, if the engine is running and you're going down the highway and a fault occurs, you will get reduced engine power, but you'll still have an engine that runs. So no manufacturer is going to shut the engine off while you're in drive, while you're going down the highway. It's a myth that if the engine overheats or if it loses oil pressure or if it loses vital data, it'll just completely shut off. That never happens because manufacturers have to be worried about the lawsuits and the safety side. So it's not only the lawsuits, but it's also the safety side. If they have a program that just shuts off the engine entirely, that could, in theory, be a worse scenario than letting the engine just run under reduced power, even if the engine's not being precisely controlled. So the accelerator pedal position will come, you'll see it in your service information as APP1, APP2. So APP1 and APP2 are going to be given a 5-volt reference, and they're going to have signal wires that come out. And those signal wires are independent wires that go back to a module. And typically the module is called a TAC module. It's not always called a TAC module. It can go to like an engine control module. It can go directly to a body control module. You have to follow the wire diagrams to see where it goes next. Sometimes this TAC module is independently located. It'll be mounted somewhere on the vehicle in between the throttle body and the pedal. Sometimes the TAC module is located as part of the throttle body. And so you kind of have to just look at service information and wire diagrams to figure out where that module is in the event you're trying to diagnose where the fault is. All of these systems are going to operate on a CAN bus network, meaning that all throttle input on your accelerator pedal position is broadcasted on a network across the entire car. Likewise, the position of the throttle plate is also broadcasted across the entire car. So take, for example, your transmission control module. Your transmission control module is going to get accelerator pedal position. Likewise, your transmission control module is also going to get the actual throttle plate position coming from the throttle body. So that's another one of the advantages of the system is we're reducing the amount of redundant sensors on a car. And we were doing this even before electronic throttle plates, but it just goes to show you how this system can be simplified and other systems on the car can then use that information for what they need. So your braking system is going to be looking at all this data from your accelerator pedal and your throttle, your traction control system, your transmission, your four-wheel drive systems, your engine's going to be looking at this, and even your radio is going to be looking at this. Your radio on your car, like wheel speed and all that stuff, kind of plays into maybe some of your volume controls. So these systems they can be a little complicated to wrap your mind around, but when you look at it from the big picture, it makes sense that they would do this. Also think about the other part here is autonomous driving. Autonomous vehicles are coming. It's manufacturers are working on this stuff pretty religiously. They're trying to make cars that can self-drive. Well, this system here, a self-driving car is going to incorporate this system. You can't have a mechanical throttle plate and a computer driving the car. You have to have a computer that can control the throttle plate. So again, we're building on systems over time, but autonomous cars are going to be using this technology as well. So we already talked about that slide. Let's move on. So your typical accelerator pedal position sensor is going to have the redundancy built into it. And so this illustration here is showing what your PCM is going to receive on voltage. So you'll notice, though, that we have two lines. We have a red line and a green line. I think there's another one. Yeah, there's another slide coming up, too. Your red line and your green line are your two sensor inputs. Your two sensor inputs are not going to operate on the same scale. That is done on purpose. So in the past, we talk about as you open a potentiometer and you move it, you change resistance. And as you change resistance, you create a different voltage drop across the circuit. What manufacturers are doing is they're designing these sensors to be skewed from one another. So they're not going to be the exact same output. That is the key to this system working. You don't want to have two sensors that operate on the same scale, because if you have a voltage loss issue, voltage drop maybe on your 5-volt reference, they're both going to react identically, and then you basically end up with a scenario where it's pointless to have two. So by skewing these, offsetting both of these sensors, if in the event one of them goes bad, or you have a voltage drop on the ground side or on the 5-volt side, it's going to skew them oddly. And so you're going to end up with the two not becoming rational. So the computer is looking at every one of these points, like a million different points, and it's comparing. So when one of them says 2 volts, the other one is supposed to be saying maybe 1.5 volts. And as it goes up on scale, now one says 3 volts, the other one's supposed to say 2.5 volts. And if you kind of get what I'm saying here, is the two have to make sense with each other at all times. Whatever the gap is in them, you'll notice that one ramps up sharper than the other, so the red line goes up quicker and it hits 5 volts. The green one never even hits like the halfway point. That is done on purpose. So that gap is going to get bigger and bigger and bigger as you accelerate. The pedal moves further and further down. That gap should get larger and larger and larger. And by that design, if there were some sort of resistance issue in the circuit, that gap would not match. Does that make sense? So that gap would not match all the way through. So as one of those sensors was at a point that the computer recognized, the other one would not be at the proper distance between it. So the default position of your throttle plate is not 0% anymore. When the engine's off, when the engine is off on your cable drive system, the throttle would be at 0%. Now, on your electronic systems, when the engine is off and there's no power, there's no voltage going to the throttle plate, it's not at 0%. It actually rests at about 20%. So somewhere between like 16 and 20%. That is another safety feature that is designed into these systems. What the computer will do when you start the engine and you give electrical power to the throttle body, it'll close the throttle plate down to 0 or almost 0. In the event you lose power while driving this vehicle, if not powered like the whole car, but power like a fuse blows on the electronic throttle control system, if a fuse blows or a wire goes bad or the electric motor goes bad, that throttle plate will jump to about 20%. And that's where it wants to sit. That's the off position, the neutral position with no current being applied to the motor. That is a safety feature in the event of a loss of power. You don't end up with a vehicle that just snaps the throttle completely shut. So if you're driving down the highway, maybe you're on an off-ramp and it's a really dangerous situation, or you're on a bridge, you don't want the engine to lose all power. So what the system will do, in the event of a loss of voltage, it'll allow some engine power. It'll allow that vehicle to run at roughly 20% throttle, which gives you enough horsepower, enough acceleration to get the vehicle to the shoulder or out of the dangerous situation, ideally. Now, yeah, if you're pulling up a big hill with a trailer, you're probably SOL. But 99% of scenarios, this is going to be enough throttle plate to get you out of a bad situation. All of these systems operate on the H-bridge design, and all that means, if you look at figure A and you look at figure B, look at the DC motor rotation. So in this one, we're going clockwise. In figure B, we're going counterclockwise. By reversing polarity, we can cause that electric motor to run in the opposite direction. That is the benefit of DC motors. DC motors, all I have to do to make it go the other direction is reverse polarity. So I take the positive wire and the negative wire and I flop them. Here's a diagram of your typical like pinout. So if you're looking at a computer pinout on a wire diagram and you're trying to figure out what wire to T-pin into to check for voltage, to check for grounds, this is what it's going to look like. You're going to get some sort of 5-volt reference. The 5-volt reference to the module is going to supply your reference voltage for throttle position 1 and throttle position 2. You're going to have a ground for that potentiometer circuit, and you're going to have a power and ground for the actual motor itself. Visually, if you look at these wires, typically like pins 5 and 3, those are the higher current wires that actually control the motor. So typically, you can visually check and see which wires are for the motor itself and which wires are for the electronic circuitry for the sensors. If you have a voltmeter, you can go in between pin 1, then 2, then 6, then 4, and you can probably figure out which wires are which without even having a wire diagram, just by using common sense and our electric theory diagnostic skills that we already have. So I think that's it for this one here. Something else just to note real quick. The book talks about it, but I wanted to make a note. If you look here, TP signal, they're not telling you, I mean, I guess they kind of are. This is definitely a potentiometer. You can see the resistance here. This is the potentiometer. Don't forget that some of these circuits they are frequency generators on the signal wires. And so some manufacturers, and we saw this in the lab, some of you were using the Picos, and it was partially my mistake for not recognizing the cars we were working on and what systems they had. But the throttle position sensors can be frequency generated. So they can be a Hall effects on, off. And so what Hall effects is doing is just making a square wave between 0 and 5 volts typically. And it's generating a frequency based off of throttle position. So some manufacturers utilize that. So here's the TP sensor. If you have a potentiometer style, you can see this is common on the throttle body itself. Your throttle position will go on 1. So the red one here is going from 0 to 5, and the green one is going from 5 to 0. And so you can look across the bottom of the scale, and we got a 0% throttle, then 50% throttle, and then 100% throttle. So one of these is coming down in voltage as we go up in throttle angle, and the other one is going up in voltage as we go up in throttle angle. All right, let's talk about the scenario, the scenarios for a failure of some kind. So most manufacturers are going to give you reduced engine power, and they're going to tell you somehow that that vehicle is in reduced engine power. Reduced engine power is also known as limp mode. Limp mode is just a broad term that states that the engine is in some sort of default safety reduction of power. It can be to prevent damage to itself, So if you had like a transmission that was slipping, you can end up in a limp mode. If you had an engine that had a really bad misfire, you can end up in a limp mode. 100% all the time, by design, no matter what, burn this into your brain. If there is any type of issue on the electronic throttle, you are going into limp mode. And you will get a light that illuminates on the dash. It could be in the information center. It can literally just pop it up as a light bulb and a symbol. All manufacturers do a different thing. So you can see here it says reduced power. Here it has an engine with an arrow going down, which means reduced power. Here you just have a wrench. So that's just like a service light. That's not a check engine light. That's a service light. Keep in mind that check engine lights, when they say service engine, that means you have an emissions fault, but manufacturers are putting other systems on these cars to illuminate a light and make a driver aware that there's an issue with the vehicle and it needs to be taken off the road and taken to a service center. There's another one. Okay, electronic throttle control. That's what that one is for a Chrysler. All right, so what manufacturers will do, if depending on how bad the situation is, so like if you were to unplug the throttle plate completely, just completely unplug it so there's no voltage at all going to it, the engine will still run. 9 out of 10 times, from my experience, and it does vary from manufacturer to manufacturer, but that engine probably will run until you shut it off. And then once you shut it off, it won't restart. It'll just block you out. And so what that design, if it's a serious enough problem, and pretty much all of these are that way, they're that serious. If the computer doesn't know what's going on, and when you go to accelerate and it gets bad data back on the throttle position, or it gets bad data from an APP sensor, if it sees any type of fault, it's probably not going to let you restart the engine. There's a good chance of it. It'll let you keep driving the car to get it to a safe place, but then once you shut the engine off, that's where you're going to get a no start. So the reason I bring that up is when you talk to your customers and you're service writing the complaint, this is the value of getting more information out of the customer than just simply it's a no crank, no start. What led up to the no crank, no start? Was the car running fine before it ended up not starting? If the customer says something like, yeah, it didn't have any power, I'd push on the gas pedal and I didn't want to accelerate, bingo, okay? You are onto something with that extra information. Yes, you're going to get trouble codes that point to the electronic throttle, so you should be able to pick up on this pretty quickly as to why the engine is not starting. Because you can get the key on, you can power up the vehicle in this case, and you can get scan tool data activity, and you can pull codes. And the codes are probably going to say something along the lines of electronic throttle plate, something, something, something. And that should be your cue as to why this engine is not starting. If you clear the codes, sometimes it will restart one time. So if you get that code to go away, that code is blocking the engine from starting. You make that code go away, you could probably start the car. So if it's sitting out in your parking lot a half mile away or whatever from, in the snow, and you don't want to push the thing in, bring your scan tool out there, plug your scan tool in, wipe the codes out of it, record them first, but wipe the codes out. You could probably start that car under reduced engine power and just maintain 20% throttle and drive it into the shop so you don't have to push it. The first time you realize this, after pushing a car in, you're going to be a little upset with yourself that you just braved it through the snow and slipped and, exhausted yourself getting a car in the shop. So not only can the electronic parts fail in these systems, but internally they can fail too. So we can have motors that go bad and sensors that go bad, but we can also have gears that strip out. So one of the things I want you to do when you're diagnosing these systems is to pay attention to the smoothness of the throttle plate opening and closing. Now, be careful with sticking your fingers inside of these throttle plates. You never, ever, ever, ever put your finger inside of a throttle plate that has voltage to it with the engine running, even if it's electrically hooked up and the key is off, don't ever stick your finger in one of these throttle plates, because if it decides that it doesn't like where it's at, it has a gear reduction motor on it, and it'll pinch your finger in there. And I've never had it happen to me, but I would imagine it would be like a rat trap, and you probably would send off some curse words. So if you want to check for the smoothness of the throttle plate, unplug it. Just simply take the harness connector off so there's no electric power connected to that throttle plate at all, and rotate the throttle plate by hand, or stick a screwdriver in there and try to feel for a roughness or some sort of skipping action. So what will happen is a lot of these gears, this plastic gear here, that's a shear gear. That's by design, it's plastic, so that way it's the weak component. And so if there were a situation where that throttle plate were to bind up, it's not that it's going to break and allow the throttle to go back to 20%, but it's going to maybe prevent a jam from taking place where the electric motor is strong enough to attempt to reverse the throttle position. So if you had something get stuck on the throttle plate, or, for whatever reason it couldn't close, the electric motor is going to try to close, and it can shear those teeth off the plastic gear, because one side is steel on the motor. The little tiny one is the electric motor. It's got a steel gear on it, and you got this little idle gear that runs between the throttle plate and the motor. And that electric motor is strong enough to rip the teeth off of that gear, and it'll keep doing that until the throttle plate actually closes. So if the right scenario took place, it could maybe prevent a throttle plate from getting stuck wide open. But here's the thing: if that were to happen, or just by wear and tear of a million cycles of this gear, those teeth will actually wear down, and what'll happen is the electric motor will go to spin the gear, and the gear will move until it gets to the spot where it slips. That's where a computer will get freaked out, because it's commanding the electric motor to open, but the gear itself is not rotating, and so the throttle position doesn't make any sense according to what it's commanded, and you'll end up in a reduced engine power scenario. And so if you want to test that really quickly, unplug power to it, try to move the throttle plate, and you can actually feel where it slips. So as you're rotating the throttle plate by hand, you can feel the resistance on the gears and the spring. And when you get to the point where it's stripped out, it'll get really, really soft. You'll feel the entire throttle plate kind of free up. And if that's the case, you've diagnosed it without any special tools at all. The other thing you could do is hook a scan tool up to it and actually do a throttle sweep. And by doing the throttle sweep, you can take a visual look down the throttle plate itself, command all the way up, all the way down, and see if the throttle plate can actually get there. If it can, it's probably not the throttle plate issue. It might be something else, like the APP sensor that's bad. And looks like we're about to the end of the chapter here. So just to recap, manufacturers have incorporated these systems to kind of reduce some redundant systems such as idle air control and cruise control. They've done this in order to allow safety systems to work more efficiently, like traction control, stability control, and also to increase fuel economy. I didn't talk about costs. These systems are not cheap. When you go to replace one of these throttle bodies, they're probably going to run your cost probably $150. Labor-wise, they're not typically that difficult to remove and replace because they sit somewhere that's easily accessible on most cars. But this can easily be a $400 repair for a customer in no time. The accelerator pedal itself is usually a relatively easy repair. Labor-wise, it's just a couple bolts and bolts to the firewall somewhere down underneath the steering column, and it's got an electrical connector that goes into it. Straightforward. Again, they're a couple $100. They're not terribly expensive, but they all fail. And it's kind of odd that like some manufacturers just have a plague of failures on these throttle plates, and other manufacturers never have problems at all. And so depending on what you're working on, if you're at a dealership and you're on specific brands, you may see a whole bunch of failures on these. Or if you're on a different brand, you might not see any failures at all. One final note before we leave here on the diagnostic side, just to kind of add a little bit to the book. If the throttle plate gets stuck due to carbon, that is one of the biggest issues as far as like maintenance goes on these systems. So over time, carbon will build up on the backside of your throttle plate. Doesn't matter if it's electronically controlled or if it's cable controlled. The PCV system, as we discussed in the last chapter, always causes some sort of carbon to build up. The issue with electronic throttle plate is it's so sensitive and you have no control over the actual throttle plate itself. On the older style systems, you would feel a little bit of a resistance. If there were carbon there, you push on the gas pedal, you can kind of feel the gas pedal fight you for a second until you broke free from that carbon. On these systems, you don't have any feedback on your pedal as to what the throttle plate is experiencing. So one of the issues with these is carbon buildup, and it's not a bad idea to offer some sort of throttle body cleaning service, you know, maybe 50,000 miles or 75,000 miles, somewhere in there, in order to prevent a potential check engine light or hesitation issue or a limp mode situation. Because if that throttle plate gets stuck due to carbon, if it gets sticky, that's going to be transmitted into like sensor data. And so that when the computer goes to move the throttle plate and it fights it a little bit, or when it goes to close it to zero and it can't get it to zero, you can end up in a limp mode situation. But 9 out of 10 times, what happens is you end up with a check engine light before it gets that bad because of air restriction. So we're reducing the amount of airflow around that throttle plate at the zero position or around 5% or so. And what happens is the throttle plate doesn't close to 5%. When it's closed, it's maybe at 15% because it's being held open a little bit. And there's a threshold to where the computer is allowing for some discrepancy there. Depends how sensitive the circuitry is designed with the software for code enabling criteria. Most manufacturers, what you're going to find is you're going to get a check engine light once you get to about 15% hang up on throttle. So when you go to the throttle goes to close and it can't close past like 15%, you're going to get a check engine light. But the reason you're going to get the code is not going to be for throttle plate. On most of these, what the code's going to be is a map sensor code. And I'm telling you this because the first time I experienced it too, I had no idea that you can get a map sensor code due to carbon deposits on the throttle plate. I have fixed so many nuances on these electronic throttle cars just by simply cleaning the throttle plate. So little hesitations to the engine, rough idles, check engine lights on for map sensor readings. And you got to think about, like, how would you end up with a map sensor code? It's all about the triangulation of rationale. So when these circuits are designed to rationally detect whether or not they're working correctly, if the throttle plate is at 15%, manifold vacuum should be at maybe, 15 inch-pounds. I'm just picking a number. But that's all electronically figured, right? So if the throttle plate is at 15% angle, it doesn't know that it has a restriction because there's carbon there. All it knows is the throttle's at 15%. And so the map sensor, it's rationalizing at 15%, I should be at 15 inch-pounds of vacuum. Well, if you have a restriction, you're really going to have more vacuum because there's no airflow around that 15%, or there's a reduction of airflow around that 15%. And so manifold vacuum might actually be at 20 inch-pounds. And so the map sensor circuitry is going to set a code for rationale on the map circuit because there's a restriction. And so it doesn't know why it has a higher vacuum, and it thinks that there's actually a problem with the map sensor, when in reality it's just carbon buildup. So on all these cars, whenever you're chasing little hesitation issues, slight idle complaints, like a rough idle, a little hesitation while accelerating because the carbon's causing the stickiness, or a check engine light for a map sensor. One of the first places you should go on all these cars is the throttle plate. And you need to take a visual look, and you might have to remove the throttle plate completely, but a lot of times if you just take the power off, unplug it, shut the car off, unplug the throttle plate, take a screwdriver, gently open up the throttle plate, and use a rag. Don't just spray carbon choke cleaner down there because you don't know where that's going. You don't want to flood out the engine. Spray it on a rag and wipe down and scrub as much of that junk off the throttle plate as you possibly can. You'll probably clear up most of your issues if they're minor like that. So, I don't know, just a few little extra tips there. That concludes chapter 22. If you have any questions, go ahead and get a hold of me on this, and I'll see you on the next chapter.